I wanted you to be able to see any simple harmonic oscillator and figure out what controls it. That's what I want. Tried to give you a framework for it and it failed. And in third period, when I was doing this exact same conversation, I purposely wrote things wrong to see if anybody was paying attention, and they failed that terribly. I'm not going to try that in here. I don't need to confuse you. I was just frustrated. They're not going to ask this question of a spring and say, okay, what's its period? What if they ask this question, which actually has been on the exam? So they have a rod that's got a pivot point here, and there's a spring attached to one end. And they set it up so that it can oscillate. Well, that's a lot, isn't it? That's a surprise. That's not a spring or a pendulum. It's somehow both. Well, what are you going to do? Are you done? I mean, is the test over for you now? Because this is a unique situation. I haven't asked this question since 1973. Could it be on this year's? Yeah, it could. So when I'm trying to say, okay, can you figure out the parts of this problem that are going to control how it moves? Are there things in here that you can kind of point to and look at the forces that act? And even if you can't break it down to like the basic physics of it, and free body diagram it, I mean, obviously the inertia of this thing's going to have to play a role somewhere. And it's a rod rotated about a pivot point that's not at its center or its end. That's going to be important. And if there's gravity involved, gravity is acting at the center of mass, like this here. All of that. Are you prepared for this one? I don't think you are, but this could be there. It's been on the test before. Or this one. This has been on the test before. It's a disc, and it's got a cable attached at its middle, and it's hanging and can oscillate back and forth like this, so that it has a kind of an angle of oscillation. And the cable is made out of metal and has a tensile strength that provides a torque when bent. That's kappa times delta theta. It's like Hooke's law for torque. Are you going to be done when you see this? Or can you find the similarities between this and the systems we've talked about so that you're not stuck? Because the first question on this one was, what do you think the period would look like? And I don't want you to be stuck. I want you to be able to say, okay, there are things about this that look similar to F equals minus KX. Can I kind of begin to grasp what's there? What would be the part on top that would be the restoring force? And what would be the part on the bottom that would be inertia? It's got to be probably that. The moment of inertia has got to be a part of it. And maybe that kappa acts just like the K value for a spring. I don't know. But can you understand that when you're faced with a new situation, you're going to have to find a way to adapt what you already know so that it will fit this new situation, or you're leaving this one blank. And yeah, you might be able to afford to leave it blank, but that's not really the goal, is it? So what I tried to do yesterday failed, and I'm sorry. But this is important. And it's more than just what's here. It's restoring force and inertia. And it's those two things together that determine how the thing will oscillate. Yes, I would really, really like it if I could get you to see the power of the second order differential equation. More important, what I'd really like to get you to do is realize that it doesn't really matter what's moving. That if it's a second order differential equation, no matter what I put here and here, it's what's there that matters. So if it's something that is oscillating its angle, fine. If that's what's oscillating, if it's its angle there, great. You guys are in E&M. What if it's the charge? It's still whatever's here is what's important. That's what controls the oscillation. That's what I'm trying to get you guys to understand, that there's this generic kind of established thing. It's generic. If you can make your system look like this, then it looks like all other simple harmonic motion systems. But I said I didn't convey that to you in a meaningful way where you could apply it. The two-spring system was elusive and so far outside the box that most of you kind of gave up, glassed over, and I said, it didn't work out. It didn't work out. So I want you to maybe forget that for a moment and understand that no matter what, you currently have two already that you know. These are ones that you know exactly what we're talking about, and they apply perfectly. This is our spring mass, and there will be spring mass systems for sure. And this is our simple pendulum. And there will be simple pendulum problems for sure. And if you understand where omega is in the grand scheme, then you can solve those problems. But they're not going to be exactly what you expect. They're going to try and come at you sideways a bit. So I want to add, I don't have it up here anymore. I'm trying to make it look like, I didn't write it down. Sorry. Today, really the final one. And that's the physical pendulum. The truth is, all pendulums are physical pendulums. Simple pendulums are ideal. All pendulums are actually simple pendulums. So the ideal pendulum, is the simple pendulum. It'd be nice to make one, but remember I told you there aren't really simple pendulums. We can't have massless rods that hold point masses at the end. We approximate them. But a physical pendulum, they're more obvious. Just take a meter stick and oscillate it back and forth. That would be a physical pendulum. It wouldn't have the properties of a simple pendulum because the mass is spread out through the entire length of the object. That's what makes it a physical pendulum. That we can't treat it like a point mass that's moving in an arc. We have to treat it as the entire mass's moment of inertia is involved in determining how it behaves. Now, the physical pendulum is a little more complicated in its design. So I want to portray it a little differently than I have here. I'm choosing something that has a regular shape because it's fast for me to draw a rectangle. But let's assume that it has a pivot point right here. I'm drawing it a little bit lower than I had it before, just to ensure that it doesn't have to be about the end. This object has a moment of inertia about that pivot point. So this could be like me holding, the meter stick, say here. It clearly has oscillatory properties. Can you believe that it's an oscillator? Looks like it, right? So I'm not surprised, but also, same thing, oscillator, just don't want to drop it. I mean, I could probably grab any object, same thing. So any object can be a physical pendulum. If we're using gravity, which we were, then there is a restoring torque that causes it to oscillate. So we need to identify where the center of mass of the object is. This distance is from the pivot point to the center of mass. And I'm calling it just X, center of mass. It's a generic term, but I can grab any object, and no matter where I grab it, as long as I don't grab it at its center of mass, it should oscillate if there's an unbalanced torque. In this case, there will be an unbalanced torque about the pivot point due to gravity acting at the center of mass. So our unbalanced force is actually an unbalanced torque. That's going to be the restoring force for our system. And the moment of inertia is going to be the thing that tries to prevent the object from accelerating. So omega for a physical pendulum, and I'm going to activate this without proof, but it's not hard to see it, is going to have the same principal ideas. Restoring force on top, inertia on the bottom. So X mg divided by I. Restoring force on top, K, inertia on the bottom, M. Now my goal had actually been for you to say, okay, net torque equals I alpha, and net torque is X, center of mass, mg, equals I alpha. Sorry. X, center of mass, mg, sine theta. I forgot to put the theta in there. And then say that, well, this is d squared theta over dt squared. And I'm going to say theta equals sine theta. All I need is to make you realize this is the opposite direction of theta. Yes, sir?
Why did you substitute the alpha for the d squared theta?
Well, I started with Newton's second law, and I'm trying to make it look like this. That's what I'm trying to do. So when I went from alpha to here, I just put in alpha as the second derivative of theta.
So theta is our axis.
So theta is what?
Is our axis.
Yes. For an object that, if we say the object is kind of doing this thing. Is that okay? And I'm trying, what I'm hoping to do here is just continue this trend here and write this as, negative x center mass mg over I times theta equals second derivative of theta with respect to time, and point out these similarities. That's all I'm trying to do. And it's not, you're right, it's not x, it's theta. But it has the same structure, so I think we can likely use whatever's here in place of omega. That's what I'm trying to demonstrate. I don't know that you'll ever have to do this on the exam, but you might. And I want you to understand that any second derivative that equals the original function, it probably oscillates. And you could probably use, no matter what portion of it is oscillating, theta, x, like I said, charge, it could be electron charge and stuff, all those things, they all have oscillatory properties, and we could probably find them. But even if you don't want to do that whole route, then just look at this part for just a minute. If we look at this for just a minute, imagine that we apply it to the simple pendulum, where this is L and this is M. Because the physical pendulum can also be a simple pendulum. A physical pendulum is more generic. So if I consider what would change if I was to draw this as a simple pendulum, X would be L and still have mg. And I would be the moment of inertia of a point mass. And when I cancel out the M and L, I get what drops down to be the same thing as a simple pendulum. So the simple pendulum has always been the physical pendulum, just simplified. Let me show you an example of how you might have to do this in class. I have a rod of mass m, length L. I hold it perfectly horizontal. I have created a pivot point at the end, which means its moment of inertia is 1/3 ml squared. I release the end of the rod. All right. I know it's written messy. I tried to write fast. We've done number 1 and number 2 before. If it's a rod of uniform mass and we release it, I'm asking what is the angular acceleration right when it's released? We've done that before. And we've also done problem number 2 before, where I've asked how fast is it moving when it swings down to the bottom. We've done that one before. I'm saying that probably on a problem like this, they'd have asked number 3, which is what is the period of oscillation of this thing as it goes back and forth around the bottom. Can you try these? I think your answer should be an M, L, and G. I bet you can do them. Try. Right here with you. What'd you do? Yes, write it down.
Well, find the angular acceleration
doing great.
I can't run it.
It's not letting you write.
I'm not.
All right, so that's where you should start. They're asking for acceleration, so that's the right place. Keep going.
Plug that in.
MG.
Sorry.
No worries.
And
Okay, stop right there. How many of you know you have to put the torque is going to act at the center of mass of the rod? So you got L over 2 times mg. Fantastic. Keep going. You're doing great.
And then you plug it in. L over 2 mg equal then for inertia, you know, it's 1/2. I mean, sorry, 1/3 L squared. So you plug that in. And then it's also output.
Okay.
So you can take out the atoms.
You just give us a final answer. You're good.
What?
You just give us a final answer. You're good.
Oh, okay. So that's going to be 2g over 2.
Perfect. Any questions, guys?
Oh, sorry, no. Yeah. 3g. Sorry.
Yes, 3 over 2.
Yeah, sorry. I had 3g over 2. Sorry.
There should be an eraser like tab on the one.
3g. My phone.
Is that 2L? Not.
Oh, sorry, 2L.
Yeah,
Sorry. I messed up. 2L.
Now we got there. Excellent. Any questions about it? All right. Alex, hands to any table. They're going to do number 2. Doesn't matter to me who. All right. All right, guys, you got number 2. Great, Zoe. What do you got? So conservation of energy. Perfect. All right, let's ask that. Do you guys understand why, in this case, H is going to be L over 2? It's the center of mass of the meter stick is what changes height. Excellent. You're doing fantastic. No, I think you did fine. So that's going to be the angular speed as it swings down towards the bottom. Conservation of energy works here. So these are the things we've done in the past. So who thinks they've got number 3? Can you hand it up to the front of the room? Now, just so you know, I'm going to point out a mistake made. Go ahead. Sorry, behind you. Point out a mistake that was made third period after we see how we handle it here in the front. Just number 3.
So I knew that T was equal to 2 pi over omega, and we found omega from number 2, so we know that omega is equal to square root of 3g over L. So what I just did is I just knew that 2 pi times 1 over omega, which would just be 2 pi square root of L over 3g.
Okay. So I'm going to stop you. This is wrong. And it's the same mistake made third period. And I think that I can find out what the problem is. Go ahead. They are different omegas. Question number 2 refers to the angular speed. That is a product of conservation of energy that has to do with the motion of the center of mass as it makes it to the bottom. That is not the angular frequency, which is based on the properties of simple harmonic motion. So if you plug in to omega for the angular frequency, which is x center of mass mg over I, you get something different than this. Because here it's going to be L over 2 times mg divided by 1/3 ml squared, all into the radical. And you'll cancel an L, you'll cancel the m, but you get square root of 3g over 2L for omega. The two omegas are not the same. This omega is the angular frequency. It lives inside the sine or cosine function. So